We're now going to look at another geometric application of integrals to volume, except this time instead of known cross-sections, we're going to look at what happens when we rotate a function or a region of a function around one of our axes. So this is called volume of a solid by rotation. And I'm going to show you two different ways to do this depending on what kind of function you have, but there are additional ways to address this. So example one, we're going to look at disk and washer method, and there's also a cylindrical shell method if you want to check that out. We are going to find the volume of the solid created by rotating the region bounded by y equals x squared, x equals 2, and the x-axis around the x-axis. So what does that mean? So we are going to take a little region of our plane. This is x equals 2. We are looking at the region between y equals, here's our f of x equals x squared. And we are going to create a solid by taking this plane region right here, that kind of solid area, and we are going to rotate it around the x-axis. So we make kind of a cone-looking solid, and it's going to come out here and look like that. So it's going to go down in the same way, and it's going to be a nice solid. So it's sort of like taking an area and making a cone. And I have another link here on the notes that you can go check out, which is a nice visualization of what this actually looks like in 3D, made by somebody with way more computer skills than I've got. So what are we going to be doing? It's going to be somewhat similar to what we did when we were looking at finding the volume of a sphere. We are going to be looking at each of these. If we think about cutting cross sections of this solid, each of these cross sections is going to be a circle. Okay, so we are going to be adding up disks, which is why this is called disk method. Okay, circles that are perpendicular to the x-axis. And so what we want to do is we want to find a of x for our circles. Okay, so some a as a function of x. So a of x is going to be, of course, pi r squared. And the working it out part that you have to do here is figure out what is our r in terms of x. How can we write r as a function of x? Well, r is the distance between the x-axis and the function f of x equals x squared. So it would be that distance here, here, here. That's always going to be the radius of the circle that's formed when we rotate that function around the x-axis, okay, and create circles that are perpendicular to the x-axis. So r of x is just going to be x squared, because we are taking the distance there is going to be x squared for all x's between 0 and 2. And then we're forming circles with that radius. So our area of x is going to be pi times our radius, which is x squared, which is just pi times x to the 4th. Okay, so when we want to add all of these circles up, we're going to be doing similarly to what we did. We're going to be taking the integral from 0 to 2. We're adding up all the circles from 0 to 2 of pi times our area of x. So pi times ax dx, sorry, not pi times ax dx, just ax dx, which is the integral from 0 to 2 of pi x to the 4th dx. Integrating, we get pi over 5 x to the 5th, and we're going to be evaluating that from 2 to 0. which gives us pi over 5 times 32 minus pi over 5 times 0, which gives us 32 pi over 5. Okay, let's look at another example. And for this example, we are going to take the exact same function, okay, and revolve it around the y-axis. So this is going to create a very different kind of solid. The one that we looked at before was kind of like a cone. So we have our x squared, y equals x squared. This time we're going to be making cross sections this way, and when we revolve it, it's actually going to be more like a kind of a bowl, I'd say, that's going around like that. So it's kind of a bowl of a varying thickness. And we're going to be trying to find the volume of that. So in this case, okay, find the volume of the solid formed when the same region is rotated around the y-axis. So since we're rotating around y, we have these, we're looking at these things that are perpendicular to y. Okay, so we're going to be adding y, and we're going to want to find our area in terms of y. So we want a function of y that is going to give us the area. So let's think about what this looks like. What we're going to do is we're going to take a slightly different view. We're going to look down at this from the top. We're going to just kind of take a slice right here. Okay, like a perpendicular slice. We're going to see what that looks like. So we have right here, we have sort of this inside that's empty, and then we have this region right here. So it's kind of like a ring or a washer. And that's what we want to find the area of at each level, is what the area of that sort of ring is. So if we think of this as two circles, we have the radius all the way to the outside, let's call that R2, and then the radius just to the inside. So the area, when we're trying to find the area of a shaded region with two circles, if we think back to, I don't know, Math 8, Math 9, this is equal to the area of circle of the bigger circle minus the area of the smaller circle. In this case, it's going to be area of the circle with R1, so pi times R2 squared, that's our bigger, minus pi times R1 squared. We can factor that out to give us pi times R2 squared minus R1 squared. Notice in this case we're not squaring the whole thing, we're subtracting the squares because we need to actually calculate the area before we can subtract. We're not just subtracting the radii, it will give you a different answer. So what we need to do is we need to figure out what R2 is, and we need to figure out what R1 is for this little slice. So we can see here R2 is going to be just 2. That's our x value. It's a constant radius, the outside. And R1, so let's go up here. So here we have R2 equals 2. R1, we want to write it in terms of x. Sorry, we want to write it in terms of y. So R1 is going to be radical y. Why? Because when we write this, this is y equals x squared, which is the same as x equals radical y. And because we're looking only at the positive part, okay? We're creating a solid that involves negatives, but right now we're only looking at the cross section right here in this positive part. So my area of y is going to be pi times R2 squared minus R1 squared, which is going to be pi times 4 minus y. So now we can go and we can actually integrate. So I'm going to be integrating from 0. This time I need to look here. So here I was integrating from 0 to 2 because I was integrating across x. This point right here is actually 2 comma 4. So because I'm integrating in y, I'm going to be adding up slices that I've sliced in y. I need to integrate to y equals from y equals 0 to y equals 4. And my little slices are going to have thickness dy. So this is going to be area of y dy. Okay, and so my area, but my area here, area of y, is area of my washers, not area of a disk. So this is the integral from 0 to 4 of pi times 4 minus y dy, which is, when I do the integral, is pi times 4y minus y squared over 2. I'm going to be evaluating that from 0 to 4. So this is equal to, when I plug in that, I get pi times 16 minus 4 squared divided by 2 is 8, minus pi times 0. So we end up with 8 pi for the volume this way. And notice, because we're adding up different solids, so if we look back at these two problems, these solids look completely different, and we actually got completely different answers. We got 32 pi over 5, and we got 8 pi. So you're not necessarily going to get the same thing adding in x and adding in y. Let's look at one more example. Okay. So we're going to find the volume of the solid formed by rotating the region between y equals x cubed and y equals radical x around the x-axis. Let's sketch a picture. So we have y equals x cubed. First thing we're going to want to do is we're going to want to know our points of intersection, because we're not given endpoints, we're not given boundaries. So let's find our points of intersection. So radical x equals x cubed. Squaring both sides, we get x equals, and we have a domain here, we have to make sure that we're using only positive x's because that's the domain of the first function. We get x equals x to the 6th. We're not just going to divide by x, get x to the 6th minus x. We factor out an x, we get x times x to the 5th minus 1 equals 0. So either x equals 0 or x equals 1. The 5th root of 1 is just 1. Okay, so those are my 2 points of intersection. So I have x equals 0 and I have x equals 1. And if I sketch in radical x, that looks like that. And x cubed on this side of the x-axis looks like that. And x cubed continues down on there, but y equals radical x only exists when x is greater than 0. So we're talking about this region here. We are going to be rotating these slices around the x-axis and creating a solid that way. So it's going to be kind of a weird little cup that's a little thicker in the middle than it is on the either the outside at the end. It's going to be like kind of pointy down in the bottom. That's going to be fun. So since there is a gap between the axis, so you see here where you have a bit of a gap between the axis we're rotating around. When we look at a cross-sectional piece, we are talking about having washers. So we have an R2 and we have an R1. So we can also see that from the x-axis, y equals radical x is going to be the further away one, and y equals x cubed is going to be the closer one. So my R2 is going to be y equals radical x. My R is going to be y equals x cubed. So R2, y equals radical x. And my R1, we have y equals x cubed. So we are going to plug this in. These are going to be washers. So A equals pi times or our a of x, because we are really thinking of this as a function of x, pi times r2 squared minus r1 squared, which is pi times radical x squared minus x cubed squared, which is pi times x minus x to the sixth. So we're going to be integrating these washers from x equals 0 to 1. That was where the distance between our points of intersection. We have a 1 here, so we're going from 0 to 1. So we're summing those up, so the volume is the integral from 0 to 1 of pi times x minus x to the sixth dx. Those are the thickness of my slices, which is pi x squared over 2 minus pi x to the seventh over 7. And we're going to evaluate that from 1 to 0. And we get pi over 2 minus pi over 7. And we're going to subtract. This is just 0. It's all got x's in it. And that gives us 7 pi to the 14th minus 2 pi to the 14th, which winds up with 5 pi to the 14th. 5 pi, not to the 14th, 5 pi over 14.